Great to see you all chose to attend this presentation of the work that I've done together with Riccardo Ferrari at the Delft Center for Systems and Control. For quite some years now, there has been an effort within companies and research to achieve fully autonomous driving. However, fully autonomous driving, where you can call your car to come and pick you up wherever you are, is still far into the future. One of the branches of research working on a more near future way of autonomous driving looks into collaborative vehicle platoons. In a vehicle platoon, the cars do not have to be fully autonomous. They only require to follow the preceding vehicle in a controlled environment, such as a highway or a dedicated platooning lane. Considering platooning reduces the necessity for navigational and path planning, as well as computer vision capabilities, because in platooning you only require speed control and lane keeping. But this simplified approach to autonomous driving can still offer a lot of the great benefits, because for the largest part of the journey on the highway, the driver's attention is not required, and cars can drive closer together, therefore reducing air resistance, fuel consumption, and road congestion. Many control methods have already been proposed that can achieve this goal. Look for example at the works by Platoons et al. In their work, it has become clear that collaboration between vehicles by means of communicating the intended acceleration can be used as a feed-forward term and can greatly improve the controller performance. However, this external communication brings with it the risk for cyber attacks, either by a local attacker that can infiltrate the communication system or by a remote attacker. In previous work, we have developed a cyber attack detection method, considering cyber attacks where the attacker can only change the communicated intended acceleration. This detection method is implemented in the car receiving the communication, where the local measurements as well as the received communications are used to feed a sliding mode observer, which provides a state estimation with corresponding state estimation error, and the switching feedback term that is used by this sliding mode observer to obtain the state estimate. By filtering this switching term, the unknown input, which is in our case the attack, can be estimated, and by comparing this estimate to a threshold, detection is performed. And we found that using this method, when only the received communication is attacked, all considered attacks could be detected before they could cause a crash. But the communicated signal is not the only signal that is vulnerable to cyber attack, as I'll show in this example. In this video, I'm going to show you a Jeep car that will be hacked through the entertainment system, and almost full control will be taken over remotely.
Okay, do it. Do it. Kill the engine.
So we're killing the engine right now.
It says park sense. Actually can't accelerate.
I stomped on the gas, but the Jeep slowed to a crawl.
It says 43 miles an hour, but I'm not going that fast.
In this fragment, we see how two security researchers remotely cut the engine and feed the car with false velocity measurements. So clearly not only the externally received signal is vulnerable to cyber attacks, but also the local measurements. Therefore, in this work, we have considered simultaneous attacks on both the communicated intended acceleration and the local sensor measurements. To this end, we have adapted the detection methods from our previous work to allow for all these possible attacks. The detection methods from previous work is extended from a sliding mode observer-based state and input estimation method, which was first introduced in a highly cited paper by, among others, Christopher Edwards. Using this sliding mode observer, theoretically exact state and unknown input estimation is possible, under the assumptions that the system has only matched uncertainties and has no measurement noise. And once exact state estimation is achieved, the unknown input can be exactly estimated from the switching term. Using this method, attack detection is trivial as the fault estimate is exact. But when the idealized assumptions are removed, the same observer is applied, this is no longer the case. Therefore, in our previous work we have designed a detection threshold with which cyber attacks can be detected, also in the case of unmatched uncertainties and measurement noise. In this previous work, we have transformed the system to obtain a measured and unmeasured part of the observer error. Then, we found that the unmeasured component of the observer error converges to a bounded vicinity around the unmatched uncertainty, and the measured part of the observer error is bounded by a maximum noise magnitude. Furthermore, we have defined bounds on the rate of change of the measured observer error. Based on these bounds, it is shown that the fault can also be estimated with bounded uncertainty, and that the fault estimate in healthy condition can be bounded by the design detection threshold. This attack detection method has much better practical applicability because it allows for more uncertainties and measurement noise, but it still only allows for attacks as an unknown input. In other words, we can still only consider attacks directly on the communicated intended acceleration and not on the local sensors. In work by Twan and Edwards, a solution to this problem was proposed. By filtering the attacked part of the output, the attack on the sensors can be cast as an unknown input to the filter state, and thus the previously designed threshold can be used to detect attacks both on the communication and on the filtered local measurements. However, this method comes with some assumptions. Firstly, the total number of attacks cannot exceed the total number of measurements. And secondly, the relative degree between the attack and the now possibly filtered measurements is 1. And under these assumptions, exactly the same results can be achieved as we had previously. But clearly, for the work that we are doing now, where we assume that all sensors as well as the communication are attacked, the first assumption already doesn't hold. And actually the second assumption doesn't hold either. And therefore, none of the same guarantees on the attack estimation and detection can be made. At least, not yet. So, what guarantees can we make on the attack estimation and detection capabilities if all sensors, as well as the communicated input, is attacked? Well, to answer this question, let's look again at what we're actually asking our detector to do. We're simultaneously falsifying all the information the detector has, the communication as well as the local measurements. And we're asking the detector to make sense of this and even estimate the attack without having any ground truth to hold on to. And then it's very logical that not in all cases the detector is able to do this. Of course, there are still cases where it is possible to detect if there's something wrong, even without knowing this ground truth. For example, when the preceding car communicates to you that it's braking, but the distance measurement is increasing, then you know that either the distance measurement or the communication is wrong. Now, in order to generalize this and see which attacks can still be detected, we'll take the following approach. First, we look from the perspective of the attacked car and design the observer in such a way that the assumptions guaranteeing correct estimation hold. Meaning, for the design only, we're going to assume that at least one of the signals is free of attacks. Then, we derive the behavior of the attack estimate when in fact all the sensors as well as the communication are attacked. Because our design assumption will not prevent the attacker from attacking all the signals. And lastly, we'll look from the perspective of the attacker and determine how harmful we can make these attacks without being detected. Following this approach, first, the observer was designed assuming that the relative velocity measurement is the one measurement that is free of attacks. Then, based on the attack estimation behavior, the attacks were split into 3 classes. Quantifiable attacks, for which estimation is guaranteed with bounded uncertainties. This class contains all attacks for which the attack on the relative velocity measurement is 0. Furthermore, any quantifiable attack always has a non-zero chance of detection. And if the attack is sufficiently large, the attack is even guaranteed to be detected. The minimum required magnitude of the attack for detection depends on the measurement noise and the system uncertainty. Therefore, by reducing the system uncertainty or measurement noise, also the guaranteed detection magnitude can be reduced. The remaining attacks, for which previously no guarantees have been provided, are subdivided into two classes: stealthy and non-stealthy attacks. Stealthy attacks are a class of attacks for which the system attacked input-output pair is indistinguishable from the healthy input-output pair. Meaning that if we only look at the input and output of the system, there is no method with which we could identify the attack. Luckily, these attacks are not as easy to implement, because in order to successfully do so, the attacker needs a perfect knowledge of the system model. Now, using our approach, the estimate for a stealthy attack will always be 0 and will never have a detection. Then, the non-stealthy attacks. The non-stealthy attacks cannot be estimated correctly, or can only be estimated with unbounded uncertainty, but they have approximately the same detection properties as quantifiable attacks. There's always a non-zero chance of detection, and if they're sufficiently large, then there's even guaranteed to be detected. Now for step 3, in simulation, one attack has been created in each class to do maximum harm to the vehicle platoon while avoiding detection. And note that the simulations only show one realization of the noise and the uncertainty. So some quantifiable and non-stealthy attacks can still be performed without being detected. But there always exists another realization of the noise and uncertainty such that these attacks are actually detected. Here we see the attack estimation for a quantifiable attack. In red we see the attack on the relative velocity, which is 0 for quantifiable attacks. In black we see the attack on the communication and the estimate of the attack on the communication. And in blue, purple and green we see the attacks on the other sensor measurements and their respective estimates. And we can see that in this specific realization of the noise and uncertainty, quite significant attacks can be performed without being detected. The communication attack goes as high as 1.6 meters per second squared. And in this specific realization, the undetected attack is also sufficient to cause a crash. Meaning that the model uncertainty or the model noise need to be reduced to make sure that the method is safe in all realizations. Then for the stealthy attack, we can see that the relative velocity measurement in red is non-zero, and that the attacks become practically unbounded, while the estimation stays exactly 0. And from this we can conclude that the stealthy attacks can basically always cause crashes without any risk of being detected. And lastly, we have the non-stealthy attacks. And here we found that only oscillatory attacks were possible to avoid detection. Furthermore, we can see that these attacks are not correctly estimated, but the estimates do become non-zero. Due to its oscillatory nature, the attacks cannot do very little harm to the system and cannot cause a crash in any of the realizations that we have performed. In conclusion, we can say that using a sliding mode observer-based approach to cyber attack detection, basically all attacks can be detected except for the stealthy attacks, which are the attacks that cannot be detected by any method using only the input and output pair of the system. Especially the class of non-stealthy attacks, for which previously no guarantees could be provided, can be detected before being able to do any significant harm to the system. And with this result, sliding mode observer-based cyber attack detection becomes applicable to a much larger range of cyber attacks, also opening the door to many other fields of application.